So this problem was on a final exam a year ago. The situation is that you have a conducting sphere, a solid conducting sphere of radius r. That conducting sphere has a charge q on it. And outside this solid conducting sphere is an insulating spherical shell. The insulating spherical shell has an inner radius of r because it touches the conducting sphere, and an outer radius of 2r. The picture doesn't make it look like that, but it is. And this insulating shell, that's the spherical shell that encapsulates the conductor that's on the inside, has a uniform charge density rho. So the same charge per unit volume here, near the conductor as here, as everywhere else in this insulator. And the issue is there's several questions here. One, find a value of rho so that the net charge on the entire system is 0. So the conductor has charge q, so the insulator has to have a net charge of minus q so that the whole thing will be 0. Find the direction and magnitude of the electric field everywhere. Everywhere means for small r, for r within the conductor. Probably you already know that the electric field inside the conductor is going to be 0, because all of the charge will be on the surface of the conductor. Find the electric field in this intermediate region, little r between capital R and 2r, that's in the insulating region. And then find the electric field for little r outside this entire thing. And then finally find the potential of the conducting sphere, this conducting sphere in the center, referenced to infinity. In other words, electric potential V equals 0 at infinity. Okay, first of all, let's find the volume charge density. Well, this volume charge density means charge per unit volume. And the way you find the charge, if you know the charge per unit volume, is you take rho, the charge per unit volume, and you multiply by a volume. So any differential volume in here, any small volume in here multiplied by rho will give us a differential value of q. And we need to add up all of those charges. And when we add up all of those charges, in other words, when we integrate over this differential q, we will get minus q. So how do we write dq? Well, rho dv, of course. A differential volume that we can use, a reasonable differential volume, would be a spherical shell. The spherical shell with surface area 4 pi r squared and thickness dr is a differential volume. Multiply that by rho. Integrate it over radius r equal to capital R out to r equal to 2 capital R. So that's what this integral is. We do this integral, we find that result. We solve this equation for rho and find out that this is what rho is. The charge density, so that the total charge on the insulator cancels out the total charge on the conductor. Now the electric field everywhere. Well, we've already said that the electric field inside the conductor is 0. That's true if you're in an electrostatic situation, which we are. No current flowing anywhere. Outside the conductor, well, a Gaussian sphere outside the conductor has no charge enclosed because the charge distribution is spherically symmetric. The electric field has to be radial out there, and the electric field times the area of the Gaussian sphere that's out here around the whole thing. That electric field times the area is the flux, and that total flux has to be 0. The only way that can be true is if the electric field is 0. So the electric field is 0 for small r, and for large enough r, er is 0 also. And so the only question is the region in between. Again, we have a spherically symmetric charge distribution, so we choose a Gaussian surface that's a sphere with radius little r in between capital R and 2 times capital R. Gauss's law tells us that the flux is equal to the enclosed charge divided by epsilon 0. The flux is E dot dA integrated over that area. E is constant over the area. The area is 4 pi little r squared, and so the flux is 4 pi little r squared times E. So this is the flux through that Gaussian surface. The charge enclosed by that Gaussian surface It's given up here. It's Q. The charge on the inner conductor is certainly within the Gaussian surface, plus the charge density of the insulator times the volume enclosed, the volume of the insulator that's enclosed. So Q, the charge on the conductor, plus rho, the volume of the insulator that's inside is, well, 4/3 pi little r cubed is the volume inside the Gaussian surface, but the insulator doesn't include the volume of the conductor, so we have to subtract out the volume of the conductor. So Gauss's law says equate the flux with the charge enclosed divided by E0. If we stick rho in from part A, then we can solve this for E of R, and this is what we get. Points radially outward just means if the charge Q is positive, then it points radially outward. If the charge Q is negative, then it will point inward. Now, finding the potential of the conducting sphere referenced to infinity, the electric field is the negative of the gradient of the electric potential field. And so we can turn that around and say that the change in electric potential is the negative of the line integral of E dot dl. Since we have a radial field, the electric field is just dV dr, and so this delta V, the change in the voltage, is the negative of the integral of E dr. So from part B, and from what we already know about Gauss's law for spherical charge distributions, the electric field outside the insulating shell is 0, so the electric potential is constant. Since the voltage at R equal infinity is 0, that's our reference, the electric potential is going to be constant all the way in to R equals 2R, so the electric potential R equals 2R is also 0. We can calculate V of R minus V of 2R, in other words, integrate inward. That's just V of R because V of 2R is 0. That's going to give us the potential of the conducting sphere because we've integrated all the way into the conducting sphere. Potential, by the way, is constant inside the conducting sphere, so it only changes between the outer surface of the insulator and the inner surface of the insulator. And that potential at the conducting sphere is just this integral of E dr from 2R, in other words, out here all the way into R. We can plug in our electric field, do the integral, and we get this value.